screen?
Yes, I can see the full screen. So from now on, feel free to start it. Thank you.
Okay, thank you. Good afternoon, everyone. Thank you for this opportunity to present my work on the EEFIT research grant. Thank you, EEFIT, for this award of this grant, which made this project possible. Thank you to my supervisor, Professor Dina Dayala, for the excellent supervision throughout this project. I'm a research fellow at the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering at UCL. And this presentation is about the assessment of partially confined masonry school buildings and interventions for improving their seismic performance. We will look at what confined masonry typology is all about, followed by some details of the field survey of school buildings in India. What are the specific typical features of the school buildings? And then getting into some numerical analysis using applied element method and how the seismic performance is influenced by interventions for improving the seismic performance, followed by fragility and vulnerability assessment. So coming to the typology under discussion, confined masonry construction is generally what is load-bearing masonry construction type, where unreinforced masonry walls are confined by lightly reinforced concrete elements at all intersections and periphery of the walls. So this idea is to give unreinforced masonry buildings a tying effect from all sides of the building. Generally, we see that unreinforced masonry buildings are, although widely used all over the world, they are very poor under seismic action. So this is a typology, an improvement that has been practiced to improve their seismic performance already. So the kind of construction involves laying the foundations and then erecting the masonry walls in stages, followed by casting the reinforced concrete elements as keeping the masonry as the formwork for them. So this enables a very good interaction and connection between the masonry and the concrete elements. So the final products looks a bit similar to RC construction, where you have concrete elements and masonry infill walls. However, there are some very significant differences when we look at their behavior and construction aspect. So the first is, of course, the sequence of construction, as we mentioned, as opposed to what we see in RC frames, where the frames are first cast, followed by the infills. We saw that in confined masonry construction, we build the walls first and then have the frames around them. And you can already see the difference, significant difference in the size of these confining elements, where in confined masonry, we have very light cross sections and reinforcement detailing. And we do not really expect a frame behavior in the from these RC elements in the confined masonry as compared to the RC frame structures. And with respect to the lateral behavior, in the confined masonry, it is a load-bearing construction. The wall itself is supposed to behave like a shear wall under lateral action as compared to a strut action in the infill walls. So we will look at the global application of this typology. It has been in practice for the last century almost now, and it's very widely used all over the world by now, as you can see in this map. There's also this confined masonry network that is established in 2008, which is promoting the use of confined masonry around the world. And as you can see, there are several national and international guidelines and building codes that are available for confined masonry construction in countries where it is very predominantly used. So, however, most of the codes adopt a prescriptive approach. So they give you the dimensions and the limits of allowable spacing, dimensions, reinforcement detailing, and so on, and have very simplified analytical calculations, such as the wall density or the in-plane shear capacity of the walls. So it can be used for a range of applications. As you can see, it's been used in single story, single housing dwellings, and also in multi-story apartment complexes. Recently we see that it's been also used for the construction of schools in many countries. And we should remember that when it comes to schools, the dimensions of the classroom, the spacing, and the size of openings vary significantly as compared to a residential building. So these can still be adapted, the typology can still be adapted for the construction of school buildings. And with respect to the specific case study location in India, we see that we do not have a current active confined masonry building code that is yet published, but there is one that is under preparation. However, the existing codes for masonry construction already suggest and recommend continuous seismic bands and corner reinforcement bars in unreinforced masonry buildings to improve their seismic behavior. So this typology, although not formally used, it is still existing in various parts of India as a probable variation of confined masonry. And specifically after the Bhuj earthquake in 2001, confined masonry suggested as an alternative construction form to RC, as several collapse of RC buildings was observed in this earthquake. And there are now a lot of recommendations and guidelines that are produced by national organizations for promoting this construction. IIT Gandhinagar, the Indian Institute of Technology Gandhinagar campus was the first major construction project that utilized confined masonry for its construction. So they have student accommodations of 3 to 4 story hostel buildings and staff accommodation housing complexes that are built using this typology in the campus. Before we get into the case study and the details of specific buildings, it's just a recap of how they behave under seismic action. And as we see here, most well proportioned walls, that is having a aspect ratio between 1 to 1 to 1 to 1 to 2, they behave predominantly in plane shear dominant behavior. And this is the most strong, the most favorable and strongest failure mode of this typology. As you can see that the load-bearing masonry starts taking the lateral loads, and once they have significant cracking, the the tie columns start taking further load. So this lets the building accept lateral load while preventing total disintegration, as you can see from this force versus displacement curve here. So, however, with respect to the change in aspect ratios and the vertical stress on the wall, also with respect to change in the material properties and connection between the masonry and the reinforced concrete elements, we can also observe flexural failure, as you can see in the second figure in the center. Out of plane modes in confined masonry, it's observed mainly in buildings with flexural flexible roofs, and also when you have a very light vertical action on the wall. However, this is the weakest mode of failure, and it is best to avoid this by restricting the spacing of confining elements. Also by improving the connection between masonry and concrete, and also the walls and the diaphragms. There are some typical deficiencies and that causing damages in confined masonry buildings. As you can see here, one of the major reasons are the unconfined openings, which then lead to partial or total failure of walls. We also see this out of plane collapse of walls in buildings with flexible roofs, where an effective connection between the wall and the diaphragm is lacking, and there is no lateral stiffness that is provided by the available diaphragms. We also see this lack of toothing or good connections in many cases, and in general, poor quality and poor detailing of reinforcement, as you can see in these figures. So we now understand what is the expected behavior and what is the kind of normal deficiencies and the damage patterns that lead to. Now coming to the particular study, this survey was carried out in Guwahati. That's the capital city of Assam in India. This is a city, and the state itself is in the highest seismic zone according to Indian seismic zonation, with expected maximum considered earthquake with a PGA of 0.36 or higher. So there was an existing database of schools available in the city, which was used for a desk study and to identify a sample of schools to be visited during this field survey. This was, and typologies mainly observed in the site include confined masonry, as you can see here, with a varying level of confinement. There were ordinary masonry buildings with no confinement and no reinforcement. There are also several RC buildings with 3 or 4 story blocks. There are a very peculiar typology where load-bearing masonry again, which is supported by steel frame, lightweight steel frames, and also this very traditional construction type called as ICRA. So this typology is proven to be highly seismically resilient, and it is lightweight. It has masonry walls up to sill level, and above that it has ICRA and bamboo based construction. So this is used for residential and public buildings in this part of India. So this, looking at the distribution of these typologies in the database that I mentioned, with the total population of schools, this is about 60% or more is said to be confined masonry, and other typologies of RC and unconfined masonry are almost equally distributed, and with some distribution of the traditional construction. And an attempt was made to maintain that ratio in the field sample so that we have a representative sample. However, we could observe these kind of additional detailing of typologies. Say, for example, within the unconfined masonry, we saw ordinary masonry or light steel frame masonry and so on. And most of the buildings, say at least 67% we visited, were lower primary schools, which is the lowest age group of the students, and the others with higher age groups and mixed categories. And at least 90% of them were single-story buildings, and most of the school compounds, at least 50%, had 1 to 2 buildings in them. So if we look at these particular confined masonry buildings in detail, we see that all of them in this sample are single-story buildings with flexible roofs. However, they lack any lateral stiffening elements such as horizontal bracing at the roof level. And we see that most of them are rectangular blocks with at least only 25% having some irregularity. They have varied level of confinement. As a minimum requirement or a minimum confinement to call them as confined masonry, we define the presence of a plinth band, the lintel or roof band, and these intermediate tie columns. And we see that all of them have openings that are unconfined, and very few of them we could observe that they have some rough interfaces between columns and masonry, which indicate having a good connection, such as you would expect in toothing. And almost all of them have no roof band. So if this was typically the case of these confined masonry buildings. However, if we have a close look at the recommendations from international guidelines such as EERI guideline of 2011 or the National Building Code of India of 2016, which has an annex dedicated to confined masonry, we can have a more quantitative assessment of how much of compliance is seen in these buildings against these standards. So we see that most of the dimensional requirements are met by these buildings, although we have significant lack in this wall density. Or another aspect that is missing is the cross wall spacing. So these are school buildings, and the guidelines are recommending for the residential standards, residential buildings. So we definitely have a mismatch of functionality and the purpose or the use of these buildings. So we now look at one particular or most common typology. As seen here, we have a 2 classroom building with confining columns as distributed here. And the material properties are adapted from literature for the lack of having done material tests for this particular study. So we are modeling these buildings on a platform based on applied element method. In this approach, we discretize the structure into rigid elements which are connected by normal and shear springs, as you can see on the figure on the left. This particular software called Extreme Loading for Structures was used, which is based on the applied element method. As you can see here, this method works by defining these springs with equivalent properties of materials that they represent. So we have these rigid elements, and all of this material stresses and strains are captured through this springs. So it can also accommodate the springs between different materials, such as springs between more concrete and masonry, or springs between bricks and mortar by equivalent properties of the springs that connect them. And for masonry, it is particularly suitable because we are able to generate the exact bond patterns, as you can see here. And the good thing about the applied element method is because we are giving the springs all the properties of the material, we do not have to predefine a crack or a failure surface. It can automatically generate the cracks wherever the material, the springs are exceeding the material strength or the strain characteristics given to it. So, and one additional consideration given here is because we have flexible roof buildings, it is difficult to have a traditional pushover analysis where we apply a lateral action at the roof level. Instead, an incremental ground acceleration method is applied, which is similar to a ground motion based seismic assessment, except that we use a monotonically increasing ground acceleration here, so that we produce a pushover curve that is similar to a traditional pushover curve. So here is the first analysis case. We call this building the poor design model, where we have very limited connectivity between the RC columns and the masonry. So we see this analysis in the longitudinal direction, that is in the x-axis of this building, which is along the long walls. We see that the out of plane walls, as you can see on the left plot, are deforming way higher than the in-plane walls, as you can see on the right side plot. You see on the top left, you see the crack patterns of this on these walls, and on the right top right, you see the strain distributions on these walls. As you can see, this is a very premature failure of the out of plane walls, gable walls. The capacity of the in-plane walls are very minimally mobilized. And we see that separation between this masonry from the concrete columns evidently. Similarly, in the other direction, in the other perpendicular direction, we see this kind of behavior. Most of the building still remains intact, while only the out of plane components above the lintel are failing. And here again, we see there is significant difference between the deformation of out of plane and in plane walls. So the first intervention, coming to the interventions, this is the final result of the capacity curves in both longitudinal and transverse direction. So as I mentioned, the in-plane and out-of-plane walls, they are acting almost like two independent components of this building. So it is meaningful to separate these two systems and then analyze them as two systems here. So we have the out-of-plane walls as this represented by the red curve, and the in-plane walls as is the green curve. And as we observed, their nonlinear capacity is rarely mobilized in this case. So the first improvement we would want to do is to improve the connection between the concrete and masonry. So this is normally available in the case of traditional confined masonry buildings, because we have these toothed edges and cast in situ concrete elements, which then produce a very good connection. But if it's not available, it might be possible to improve this connection by additional retrofitting measures such as FRP or ferrocement, as you can see here. So assuming that we have improved the connections, now we look at only the transverse direction loading repeated in this case with better connections. So we see in this case, it is similar to the previous case, but we see that more of this walls, both out of plane and in plane walls, are mobilized in this case. And you can see that the in plane walls start to mobilize some of their nonlinear capacities. You can see in the bottom right. So as compared to the previous case, you can see here that this case with better connections have more deformability, and in the transverse direction, it also has better strength capacity. However, we still have a lot of difference in the deformation of in-plane and out-of-plane walls. Now, coming to the next intervention strategy, which is to improve the confinement. So here we have added additional confinement around the roof level, at the roof level and at the sill level. So we call this building a medium design level. And here we have confinement around openings because of the sill band, at least partial confinement. And in practice, this is done, as you can see here in these figures, these additional columns with some dowel connections to the masonry can be inserted in an existing building. And similarly, the tie beams, as you can see on the figure on the right. In this case, the medium design case, we see an improved performance where, as you can see, most of the capacity of the building is now mobilized, and we see there is a full participation of the in-plane walls in this case. And we see that much of the out-of-plane and in-plane wall capacities are already mobilized. So here is the final capacity curve from this case. We see this significant difference and improvement in both longitudinal and transverse directions. Coming to the final intervention, as you can see in the previous case, although this improved quite significantly, the out-of-plane walls did have much larger deformations as compared to the in-plane walls. So in an attempt to control the deformations, it is possible to add some bracing, horizontal bracing at the roof level, which is also recommended by guidelines in buildings with flexible roof diaphragms. So in this case, when we do this analysis, you can see here that the deformation is simultaneous in both in-plane and out-of-plane walls. And at the point of collapse, you can see that both of them are comparable in terms of their total deformations. And you can see that it's the in-plane walls that are taking most of the loading now, which is very similar to a box type behavior that we expect. So this design, we would call them high design. And in the high design case, we see that in the longitudinal case, there is a significant improvement in the stiffness and the strength properties, and also the deformability. And in the transverse case, we see that it is arresting the local deformations of the out-of-plane walls. Instead, it is better distributing the capacity between the in-plane and out-of-plane walls. And you can see that these drift limits that are marked on these capacity curves, the slight damage, moderate damage, extensive damage, and collapse damage, these get closer and closer as we improve the seismic design level. So if we compile these results and see how they perform from an overall, improving the design level from poor to high, we see that there is a steady increase, improvement in the total base shear capacity. And when we look at the performance thresholds, we see that the first two cases, the poor design and the case where we just improved the connections, let's call it the low design case, the in-plane walls are not participating in the nonlinear range at all. So we have ignored them in this analysis. And another observation is that the medium design case, especially in the transverse direction, that's the Y direction, we have a much larger deformation as compared to all other cases. So once we have this capacity assessment already done, we can then continue to do a fragility assessment. And as we mentioned here, we would split this building into two component systems, that is the out of plane and in plane systems, and convert them to equivalent single degree of freedom systems. To obtain their capacity curves in the space of spectral acceleration and spectral displacement. So this, when combined with the seismic demand in the same ADRS space, we are able to produce these performance points, which then with a regression generates the fragility functions. So these fragility functions for the poor design case is on the left. We see this black line on the graph is the level of maximum considered earthquake in this region. And you can see that the buildings are, the building is much beyond the level of moderate damage, and there is a high chance of extensive damage, but which is slightly improved by the connections. As you can see in the figure in the right, the building is still beyond the moderate damage. However, the chance of extensive damage is reduced. We should, however, keep in mind that we are talking about school buildings, and they should ideally have an immediate occupancy level, which is below the moderate damage level. Coming to the next case of medium design with better confinement, we see that in this case, we still have high chance of moderate damage. However, the chance of extensive damage is very minimal, which is further improved in the high design case. So in the high design case, we have a good chance of the building staying within the moderate damage limit, and there is absolutely no chance of having extensive or collapse damage at this intensity level. So for the sake of completeness, we can also look at the in-plane walls in the medium design and high design cases. So we can see that they are already well, they are very okay for this level of seismic intensity level. However, this is not completely meaningful, because we know from the analysis videos seen before that the out of plane walls would have already gone beyond this damage state, and the entire building may not be useful. So you can see here a compilation of the fragility parameters. As we can see, with the mean value of the intensity level corresponding to each of these damage states are improving as we improve the design level. Coming to the last component, which is the vulnerability functions. So this is a component-based fragility vulnerability derivation, where we use the fragility functions that are derived to generate the vulnerability functions. So now on the y-axis, you can see the mean damage ratio. And on the x-axis, you can see the intensity measures. So you can see in this case where we still have the system separate, that the out of plane and in plane systems kept separately, we have the poor design, which is having the highest vulnerability, and the vulnerability reducing when we go from poor design, low design, to medium design and high design. And here in the dotted lines, you can also see the in-plane vulnerability functions. So these the figure on the right, it shows you the global curves for the medium and high design cases, which is generated by combining the in-plane and out-of-plane walls in proportion to their masses. So you can see the improvement obtained from poor design to the medium and high design cases, which is multifold. So just to conclude, we from this analysis we have understood and quantified actually the improvement in seismic performance of confined masonry buildings with each of these interventions that were proposed. So based on this, a decision chart was prepared to understand what is the available design level of these confined masonry buildings, purely based on visual inspection. So if you can identify that there is good connections, required wall density or additional bands, and the nature of diaphragms, whether there is a horizontal bracing or not. So based on these parameters, we can then assign seismic design level. And as a next steps, we have taken this forward to use these fragility and vulnerability functions in system performance assessment. So now we have been looking at schools as independent entities. What happens when you consider several buildings in a single school compound and then several schools in a region? So the performance and resilience of school education infrastructure comes into play, and this kind of physical assessment is really useful as an input to system performance assessment. And secondly, this is now also expanded to multi-hazard interactions on structures. So interactions such as frequent and annual flooding followed by seismic events. So this is all from me. Thank you very much for your attention. And if you are interested in knowing more about this work and work that has come up after this particular stage of work, please refer to these publications. Thank you very much.